All right, so good evening, everybody. Thanks for joining my talk. Thanks, Li Gang, for the invitation and Xianxi for the introduction. As she said, I teach at HKUST in Hong Kong. I'm originally from Brazil, but now I've been living in Hong Kong for, I guess, 16 years. So it goes very fast. So today I'm going to talk about one of the research topics that I did recently with one of my students and colleagues on shape-inspired architectural design. And this is a joint work with my former advisee, Diana Wei-Dan Chung, who I think is also here. She's the primary author, as well as Pengbo Zhang and Professor Jay Joneja, also from UST, who we jointly co-advised Diana with, and has also done a lot of work on architecture and different geometry projects. Diana now moved to Shenzhen University. She's now a research associate professor there at the AI lab. So she's back in the neighborhood. So we hope we can continue working together on interesting geometry projects and also together with Ajay as well. So for those who are in Shenzhen and interested in geometry projects, Diana would be a great person to get in touch and to discuss with. All right, let me get started. Okay. What happened here? All right. Okay, good. I thought I got stuck in the first slide. Okay. So before I go into the topic, I'd just like to give sort of a general high-level overview of my research, just to give an idea of my background and the kind of problems that I work on. Most of my work has been on rendering optimization, how to make 3D scenes for 3D interactive applications render as quickly, as efficiently as possible on the display. And I try to look for interesting problems and sort of the intersection of geometry and efficient rendering. So basically how to process geometry so that it improves the efficiency and in some way also using GPU optimization. So this is my major area. And along those lines, I worked in a bunch of different methods for geometry level of detail, including some GPU only LOD techniques and methods to texture map LOD representations, such as you can see in these two animations there. And I also worked on methods to amortize the rendering cost of a multiple frames. So use shading results from previous frames through reprojection to improve the efficiency, minimize the shading cost. Other areas that I worked on related to this had to do with geometry preprocessing to reduce overdraw on rendering so you can maximize front to back rendering, again, to improve efficiency. And the general theme on these projects as a whole, it's mainly to try to come up with optimizations that are very general and they're applicable for different applications of rendering, right? So they are sort of native using the GPU and algorithmic challenges that improve rendering in general. So more recently, I have also been working a lot on imaging problems. This includes problems such as image morphing. You can see there on the crazy morph there on the bottom left. And the idea of that work was to design a fast interactive algorithm to generate customized morphs with as little time as possible, also as little interaction as possible by the user to get immediate feedback. I also worked on a few more vision-related problems using learning. These were mostly on document rectification, image colorization, cartoon synthesis, and also image compression. In the case of this latter one, specialized for low energy hardware. And finally, we also did some work on gigapixel imagery, particularly being the first technique on this domain to be able to generate gigantic looping videos, such as the one that you can see on the right there. It's actually a video that loops. I don't know how well it shows up on Zoom, but it's basically a video that's looping, and that's over 1 gigapixel in size. So this is kind of the general areas, the kind of problems that excite me, that I'm mostly interested in general. But today, as I mentioned at the beginning, I'll focus on one of them. And this one is a bit more related to architecture. It's the work that we did on shape-inspired architectural design. And I think that this topic is a bit more geometry, pure graphics, and among the recent ones that I did, and it'll be a nice fit for the seminar. So that'll be the focus of the talk today, and I'll be able to then go into a little bit more details on it. And hope you'll find the method that we describe and also the applications fun and interesting. All right, so let me get started. So basically, in this work, we try to address essentially the very early process of the design of big architectural buildings, such as the one that you see there, which is the National Center for the Performing Arts in Beijing. And this is often a very daunting task to take on. It involves several stages of planning. Sometimes you have to iterate over the stages multiple times. But one can break this down into a few sub-problems. In the case of the Center for the Performing Arts, first there was the design requirements on 3 main halls, which they had to do, such as, for example, their size and their height, for example. And the architect also developed his main idea in some initial drafts of how the shape should look like, the initial shape, which is shown there on the left. And then experts in different areas would work together to make a prototype of the building based on this model designed by the architect and the overall inner space structure that's needed, that's shown over there on the right side. And then they have to further design the final building, considering several trade-offs, including this trade-off between interior shape, how nicely the interior shape depicts what they want, and interior needs of the building, right? As well as the surrounding regions, right? And this particular slide, you can see the arrows, the blue arrows to the right show from the early concept to the final design. Okay. So there are also many details related to the fabrication that would come afterwards. If you notice, I didn't put it in bold there. I'm not going to talk about these today. But basically, for example, designing panels and the frame structure and things like this would come afterwards, after this. But decisions related to that may also affect the original exterior modeling and interior planning design. Okay, but in this talk, I'll focus on the first two. And we'll give it a sort of an interesting visual twist. It's a very special kind of design for the building that's specific to our problem. Okay. So in the first step, I'll propose basically a new tool for early conceptual design of a facade of the building. And then we basically discuss extending this problem to also consider the internal space planning during the optimization. So to better motivate what I'm going to talk about, let's first take a look at some of these real life buildings that were mainly inspired by non-architectural shapes. And you probably can recognize some of them, if not all of them, right? At least two, I'd say you can probably recognize there. On the top left is the famous Taipei 101 building, which is inspired by bamboo shape, right? So you can see there. On the top right is the Burj Hotel. It looks kind of like a sail of a ship. Well, not kind of like completely like a sail of a ship. And in the bottom there, you can see the Olympic Pavilion in Barcelona, which is sort of emulating the shape of a goldfish. Okay, so some of these are famous and probably familiar to you, but there are many other buildings that have sort of these organic shapes, and architects try to replicate them in the design of the building. Okay, so next, let's focus on this aspect from the previous slide, which is the design of the exterior shape of the building. So in this case that we have on this slide is the Guotai Opera House in China. And the final design is the one, is basically this red building over there, right? And it's modeled based on this design, on these draft designs that you can see a little bit to the right there. But if you look carefully at the images and look on the right side, you can see that the 3D model doesn't really match that shape exactly from different viewpoints in general, right? And the reason why this is the case is because when you build the building, you have to obey some rules to guarantee that the building is not going to fall, right? That the building is going to be feasible. So there are lots of specialists involved in that process, structural engineers that try to refine this design and to find a final solution to the exterior shape and inner space that can be built, that allow for construction. Okay, So basically in this work, we tackle the problem of designing the building that adhere to multiple visual shapes as input. So not just one, an architect will be able to provide multiple interesting shapes that from different viewpoints, you get the building to look differently. Okay, that's essentially the idea. Following this idea, this scheme, the system will take 3 images as input and then generate the building automatically, allowing some user interaction to further fine tune or improve it. Okay, or actually allowing the user interaction to set an initial setting and then optimize it to get to a valid result. So this aquarium building that you see there looks like a whale here on the first view. And then as you can see, now it looks a bit like a shark. And now as you go to the top, it looks like a eel, right? Or like a sea eel in some sense, right? So, oops, let me go here. So basically, to accomplish this, we basically try to generate a voxel model according to the silhouettes, to try to preserve the silhouettes so that when viewed from different angles, you get the correct look, right? So in the particular case of this optimization, although this can be generalized, but in this optimization, we employ 2 cameras on the ground, since usually you view the building from the ground, right? And 1 camera from the top, which is essentially the footprint of the building. And then in our modeling system, you can see the 3 user input images there on the left, right? And we consider a bunch of different aesthetics and structural requirements into an energy function that we devise to evaluate to evaluate the quality of this design, right? The user can adjust camera positions, image positions, image scale to gradually decrease these objectives, right? And these objectives are shown on that scroll bar there. If we have time, I'll show this in full screen later with more details for you to see, okay? So we have several optimization algorithms, and we can invoke these optimization algorithms to adjust whatever input the user has selected, whatever settings the user has selected, to come up with hopefully a nearly global solution at any point during the design, and then the user can further iterate on that to improve the result. Okay. Okay, so this is basically the result after the optimization. You can see that the optimal ground views are not orthogonal anymore there. The user can actually constrain the view ranges based on where they want the model to be, okay? Then we make a voxel model based on the final camera and image parameters that we have. And we will later talk about converting this into a mesh model, right? And that's what we do here, but we'll discuss it later in a little bit more detail. And then we apply a smoothing algorithm that will consider specific architectural requirements, such as, for example, having a flat roof, a smooth shape, and so on. So we'll go over those in a bit more detail. And finally, here is another concept design. And this tries to look at the shape of a mountain, the Sphinx, and the moon, depending on where you look at it from. So there's a lot of work in the literature trying to model a building from input photographs and try to adhere to some visual representation of features of the building. In this work, we tackle a very specific problem that's more precise on shape matching from multiple views. So we want the building to adhere to shapes that are different, that can be very, very different from very different views, right? So this was inspired by the shadow artwork from Mitra and Polly, but it has specific design constraints, considerations for architectural shape design, which is the target that we focus on here. Okay. So let me, oops. Okay. So that was the overview. So let me go through the pipeline now and how to generate the initial design of that Egypt building. Okay. So we start with 3 shape templates. In this case, we have the Sphinx, the mountain, and the moon, right? Initially, you have 3 cameras that you place in default positions, in this case, orthogonal positions. Then we encode several architectural requirements into the energy function, and we'll go over those later. Then we employed the proposed search optimization that we devised to achieve some approximate global solution for this function. And then we export the final voxel design that has the solution. All right. So in addition to that, the system also attempts to provide initial arrangements of the internal parts, of the internal structures inside that building. And for that, we use our proposed search optimization algorithm, which basically tries to fit in all the interior spaces in the building. And then we also finally give an option to make an adjustment to the exterior shape to fit those changes in the interior if necessary. Then given the final 3D voxel model that we have, we use marching cubes, and then we get a mesh, right? So we get a surface mesh from that. And then we apply a smoothing algorithm that is specialized to this kind of architectural shapes. All right. So now let me describe a bit more detail each of those. So first, we're given a single 2D shape, right? So we can project the shape template there into this 3D sort of voxel silhouette, this cone view that you see there, right? Then here we add a second shape a little bit to the right there that's shown in blue, right, in the middle figure there, right? And as we increase the number of shape templates that we have, we can create this visual whole, which is basically their intersection, the intersection of these shapes, right? Note that as you're making this, adding more shapes, these multiple images may not be compatible in creating a visual whole that's consistent, right? So we may get an error on some silhouettes of the intersected model. And in this particular case, it's very visible there. You can see that part of the Sphinx is missing there, the top of the head. You don't see it, which was there, right? So that's because it got basically cropped over here in the projection when creating this shape, right? So there are errors, and the goal is to try to minimize those errors. Okay. So again, as the number of shape templates increase, finding appropriate image and camera positions could become harder and harder. And a lot of work has worked on trying to analyze and reduce those distortions in order to get a match that's more accurate for all those input images. And unlike those techniques, which mainly use shape morphing and modify the contours of the input images, we explore changing positions of cameras and images. That's sort of what we do in our optimization. It's efficient, and it also helps improve the quality of the final silhouettes. And we measured error between those and the original images when coming up with our final object model. Okay. So as I mentioned, the position of the cameras may affect the result, and there may be some practical requirements from the designer or the architect. So these can be set. So the user can set a range where the motion of the cameras. Okay. So on the system, we consider several parameters for both the cameras and the images. Okay, so this is a big parameter set, and can make it for both orthogonal cameras and also for perspective cameras, right? So orthogonal cameras X sub O there, and perspective cameras is X sub P there. And these are basically translation, scale, viewing angle, and distance parameters in the case of the perspective projection. And given the value of these parameters to measure distortion, we take the sum of the squared pixel-wise differences between the original image and those resulting from the visual whole of our output, right? And this is essentially normalized by the number of pixels and gives us the error in reconstructing that particular shape, right? So that's what we call the shape template integrity, which is how accurately we can reproduce a particular image. And we do that for all three images, right? Okay. In addition to having this aesthetic requirement on the silhouette, on the contour of the images for the shape integrity, we also have a physical simulation on the voxel model to analyze and make sure that it's structurally sound, that it won't collapse, right? So if you can see on the top there, the level of instability of the voxels visualized from blue, which is fine, and then to red, which is not fine at all, right? So I won't have time to go into the details of this, but we basically approximate the stress on the voxels using a physical simulation. And that's discussed in the paper, which I'll provide the link at the end if you guys are interested in learning more. This floater volume, which is another term there, measures the number of connected components that you have. So we don't want a component to snap off when we compute the visual whole, right? So we have this black pixel there, which is something that's out in space. From this view, it's not as visible, but it's basically disconnected from the model. So basically, we don't want that. So we penalize things that break the model, right? That basically partition the model into multiple components. So then we take a sum of all these measurements, the shape integrity, the floater, the structural integrity, to come up with an energy function. Okay, we also consider the total volume, which can or cannot be considered depending on the constraints that the user has. All right, and this essentially gives us an energy function that we minimize, and the weights can be managed by the user when they design the system, or when they design the building. So as you can see, the model is highly nonlinear, it's non-convex, it's discontinuous. It has basically lots of these different terms. Some of them based on the physical simulation. They have to simulate for every candidate shape that you have. So we basically investigated a bunch of probabilistic techniques to get an approximate global minimum. And we explored things like simulated annealing, genetic algorithms, PSO, and we found that the Cuckoo search algorithm turned out to be a suitable choice for this problem, and we further modified it to this particular application. So Cuckoo search is basically an efficient optimization algorithm that's kind of acutely inspired by the behavior of cuckoo birds. Okay, so they basically lay their eggs potentially in other birds' nests, and then they may leave, right? So then the other birds can come in, and basically when they see it, if they don't find any suspicious eggs, they'll nurture them, they'll keep them, they'll grow them. But with some probability, they will figure out that these eggs are not theirs, right? And in that case, they will abandon them or remove them from there, and they will raise their own, right? So as you can see, in some situations, you will keep the solutions, you keep what the other birds drop there. In other situations, you will replace them with their own. Okay, so now done with the birds, back to the optimization. So basically with a set of solutions randomly initialized in the algorithm and placed in these different nests, right? We can iterate between two steps to update the eggs in these nests, which are our candidate solutions, right? So for this first step, we generate a new solution, which is there's X prime, based on an existing solution in a Levy flight, which is a variation of a random walk with some distribution properties. And this will apply sort of a modification or perturbation on the parameters of that solution. And then that solution is better than the solution that was on some other random location xj, then we replace it. Okay, so that's basically the idea of this algorithm. So we mutate some of these eggs and throw them in some other random location if it's better, if it actually makes the result better. Then for the second step, we also apply a mutation strategy, which mutates each existing solution with the given probability. And when we mutate a solution, we mutate it proportional, considering the difference between two other random solutions. Okay, so we look at the difference between two other random solutions in this mutation, apply some fraction of the distance based on a random number into our current solution, right? As things converge, solutions become more even, these mutations become smaller and smaller as we iterate through this algorithm. Okay, so the original Cuckoo search algorithm is actually quite efficient. But for the second step, one of the things that we notice as we're working on this project is that instead of mutating all the parameters using the same probability of mutation, we only mutate parts of the parameters that yield some better performance, right? So the parameters here are the V's, right? So you have all these V's here. And instead of mutating basically all of them, we just may mutate some of them. In this case, V1 and this one here, right? The last one. Okay. And also different parameters may have different levels of importance. Some may be more important than others for mutate, or some may lead to a better solution if you mutate them more. So we explored different choices for that and assigned different probabilities in order to improve the performance. And you can see them in colored font there, that some parameters will mutate by a larger amount, or actually more with higher probability than other parameters, and some may not mutate at all. okay? And the paper has more details on how we choose what you mutate and also the convergence of different choices. At the end, all of our designs use this modified search that I described. Okay, so now we have a voxel model that we constructed from that original optimization. You can see it there. It's on the top right over there. And we added this intuitive interface to add some different inner space elements to for users to incorporate in their interior design, basically. And you can see it's a cuboid, a cone, a cylinder, and a half ellipsoid. Okay. And the user can add or make modifications to the size, 3D locations, orientations of these basic units based on what they're designing, on the rooms, on the building they're designing, what they need, right? So they figure out which of these shapes is closest to the shape that they need, and they would use that as a bounding region for the shape that they will use in their building. Okay. So here we're adding basically 3 units in this example. We're adding 2 red cuboids and a green cylinder. Since architects may prefer to place rooms on certain specific floors, for example, you may have an auditorium and you want the auditorium to be on the ground floor, we basically fix them to the floor, and the parameter set of things that you can optimize is basically the planar location and orientation of each unit. And that's basically these UIs here. You have UIs for different units. And the union of these UIs is basically the parameters that you can basically optimize. Okay. Then to measure the quality of this space arrangement, we essentially want to consider 2 things. One is what fraction of the units are outside of the building. That's bad, right? So you can see this green shape here is outside the building. You cannot have that. The units need to be inside the building. And also so that's one thing. And the other thing is the collision of units. And that's an example there on the red case there, right? So you also don't want units to collide. They're independent, right? So you want to seek solutions which will include all of these elements inside the building and not colliding. And we use the same optimization that we described for the exterior design to place these units with these new parameters, to place them in a way that they don't collide with the building. Okay, so basically consider a weighted combinations of these terms. We also have a more elaborate version of this, a multi-objective function that also normalizes these errors within each individual unit. And the reason for that is because then small units would potentially be ignored because the error is very small, but if you normalize them, then they're not ignored. So the paper contains more details on this variation. Then it's multi-objective because you want to basically optimize for the entire shape, but you also want to make sure that you don't downgrade elements that are too small. So if you're interested in learning more about these details, the paper discusses a multi-objective function that addresses this. Finally, we provide another option to examine the possibility of making all units entirely inclusive inside the building by perturbing the outside model again. So we allow some perturbation on the original external shape if an object is just barely not fitting the model, right? It's just outside, like in this example there, right? So in our examples, we did a perturbation about 10%. We allowed them to grow by around 10%. If the algorithm after this and after all these steps cannot obtain a solution in which all the buildings are inside, that you have 0 energy for this case, then the user is essentially suggested to change the size of the space units or the shapes to make this happen. Okay, so now we have a voxel building, which has the shape that we want and also has the internal units, right? So the next step here is to apply marching cubes to get a surface mesh, to get basically a mesh of this model. And usually most common architectural designs would, especially those that are modeled after organic shapes, they have mostly smooth surface with a few shape defining sharp creases that are very important to define their shape. And they also have roofs that are nearly horizontal, right? Or balconies at the top that are nearly flat, right? And also, you can note from the example of the mesh there that it has lots of noisy areas, and this doesn't satisfy these requirements, right? You can see the roof is not flat, and you have all these undulations and noisy areas. So we explored a bunch of different smoothing techniques, but none of them were specialized enough to achieve the specific goal that we have, especially the controllable generation of a flat roof while keeping the overall shape mostly smooth except on creases. So we basically introduced a new smoothing framework that considered some of these techniques and explored some modifications to them. So we first considered the mean normal filter. And the basic idea here is to traverse the one ring neighborhood of each face to get a mean neighborhood normal. Okay, so that's GI over there. But this approach not only removes the small scale noise, but also important edges, right, or important creases. So to overcome this, we explored the idea of a deformable kernel that considers a wider neighborhood. And by considering a range of 2 ring neighbors, we basically have a bit more flexibility in adjusting the overall shape. Okay, so the way that this can be accomplished is while traversing each neighbor Fj of a neighbor of our face Fi, we interpolate the face normal of Fj with the normal of one of its neighbors. So it's two neighbors away, in that case, Fk. Okay, but we only pick one of its neighbors, a randomly selected neighbor Fk for efficiency. And since the algorithm, we run it iteratively, we eventually, by running enough iterations, the algorithm considers the information of the 2 ring neighborhoods because you pick a different random face each time, right? And so it can get to a high quality solution in less time. That's we can achieve that result by using this approach. This may still have some undesirable artifacts, like smoothing out details and some creases that we may want to keep. So to address this, we also introduce a weight, basically W, to basically measure the normal similarity, and W reduce the impact of normals that have significantly different orientations than the ones that we are basically smoothing. Okay, so this shows the effects of each of those modifications, or the combinations, different combinations of different modifications. And the last one to the right is our result, and you can see that we remove the noise and preserve the edges of the original model, which was really, really bad here, right? So this one, in this extreme case. But there's still some undesirable small creases there on parts of the surface, right? So that's one problem that we still have. And an additional consideration that's important also is the flat roof, right? So we want to have flat roofs. It's common to have flat roofs on building. It's usually desirable. So it's important that our smoothing algorithm will smooth out the roof and keep it flat as much as possible, right? So we want to consider both the overall smoothness as well as the flatness of the roof. So basically we devised a flattening scheme and basically also combine it with the bilateral normal filter. Essentially, the basic idea of this is that we snap the vertical normal to snap our current normal to the vertical normal if the current number is close enough to it, right? And there is sufficient normal variation, then we treat that as being the axis normal or the vertical normal, right? So that's what we do here. So that's one part. That's basically this part that maintains verticality, right? So it maintains a flatness at the top. And additionally, we also apply a bilateral filter on the normal in order to make sure that we can smooth while preserving the creases, right? And this is from Zhang 2011. And essentially, as a bilateral filter is, the influence of the neighbors is based on variations, on differences, in this case, the normal and the position differences of the neighbors. And the paper also contains further details on how it's computed. So here's the performance of the flattening step. As we change the parameters on verticality and normal variation, you can see it achieves different levels of smoothness, right? So verticality, if we increase verticality, then you can see that it becomes flatter there, right? To the right. And if we increase the constraint on normal variation, it becomes overall more smooth on the bottom, right? So you can explore those variations, explore those terms to get the result that one wants for the building. Okay, so after we obtain the filter this basically field of normals, right, which we call GI hat, GI bar in this case. Then we want to perturb the vertices to match those filtered normals as much as possible, right? And this is done iteratively. So at every step, we update the normals, we process the geometry, update the normals, process the geometry, right? And to process the geometry, we use the method described by Zhang. It basically considers the neighbors when moving the vertices in an attempt to match this desired normal, right? And also tries to preserve the creases. So on the right over there, you can see the whole framework. So given some kind of a bumpy match, we first apply our approach, then remove the undesirable creases and generate the flat area using this bilateral normal filter with the roof flattening. And then after that, we perturb the mesh to match these filtered normals. And then we iterate this until it converges, or until we find a satisfactory result. Okay. And these are some of the results of our general approach from the beginning, from the Cuckoo search. So now we're going to get into the results part of the talk. So you can see that basically our approach, which is the final approach, which has all the modifications, is the blue line. It's like around 5.5, so it's clearly better than some of the others here in these examples. And the original Cuckoo search is over here, right? Is this one here. So you can see it already does a little bit better than the other optimization algorithms that we explored, right? Like simulated annealing, PSO, and generic algorithms. But with our modifications, we can further reduce the cost of maintaining our goal of that minimizes that energy function. Okay. So now we can see some final results, some cool final results. So here are 4 architectural prototypes that generate with this method. So we start one by one. So we start here with the Egypt one. So it's based on the 3 binary images that you see there as the insets at the bottom in the rendered images. In the first row at the top, on the left, you can see the default settings still with the orthogonal cameras, right? You can see that it's not so good, the building that he creates. He has lots of problems, including some stress over here and some disconnected components over here. After we do the optimization, we get a much better shape, right? And the viewpoints that give this shape are these viewpoints over here. Okay, so these orientations, they give the best shape. The values of these energies or integrities before and after the optimization also shown there. So you can see that in red, all the integrities get reduced. The volume goes up. This can be scaled if needed, or it can be constrained. But you can see that it matches the images much better, and it removes the structure integrity problems that were there. Now here we have the result on the Aquarium. Okay, so you can see that you have very nice shapes visible on the output. It looks much like the original there on the output, on the final design. This is a design for possible future ACM headquarters. We're in talks with them to do that. No, I'm just kidding, we're not. But it would be nice if this was the ACM headquarters. And as you can see, the initial design is under great stress over here. And we can optimize the building. It adds some support. It puts more voxels and adds more support on regions that are needed by modifying our parameters in order to get a resulting shape that still looks like ACM, but it doesn't have those problems, right? It doesn't have those structure integrity problems. This is a bird shape concept design. And this could be also a nice building for an aviation theme, maybe an airport. I don't know if it would work too well for the airport because these are off a little bit high on the air there. So I don't know if that will work well to connect to the planes, but maybe a smaller terminal or maybe some other theme for aviation. It could be an interesting design. And that's mainly it. So basically, to summarize, I give a brief overview of the research that I do here at UST. And then I focus on one work that was a bit more geometry oriented. It was an architectural design, and picked this work because I think it has some interesting visual results. It's practical, and hopefully architects will use it in the future. And the goal here was essentially to create this practical system to assist architects and make concept designs from these given template shapes, right? As well as allow this arrangement of interior spaces. And to achieve this, we introduced this Cuckoo search algorithm. We had different energy terms, considering different requirements, architectural, structural, and how it preserves the shapes, right? And we designed this modified smoothing algorithm that was specialized for this application. Okay. There are a bunch of areas that are interesting for future research. A couple of them are specialized to improving this method, which would be, for example, to speed up the process, either of the computation of structural integrity, which is the bottleneck, or parallelization in general. And these are more specific to this technique. But we would also like to explore considering external views from inside the building, looking out into the city landscape as potential optimization goals. So further explore methods to quantify the quality of these surrounding views from different points in the building, and consider that as we do the optimization. And finally, we would like to explore its usage in the industry and hopefully see some uses of this in the real world. We conducted a user study, which is in our paper, and architects generally found the system interesting and practical, and they considering using it for preliminary design on some of their future projects that they may want to have the building look certain ways from different views. Okay, so that's what I have for today. Hopefully you guys enjoyed the project, that these are the references for the works there that I discussed in the top. And thanks very much for your attention, and I'm happy to take any questions that you guys may have. Thanks.
Thank you, Professor Sander, for the nice talk. So is there any question from the audience? Well, okay, maybe I start with my general questions first. Well, my first question is related to the computation efficiency. So so for the concept design, how long will it take to generate the final 3D shape?
So it can take quite a bit. It can take minutes or even hours in some very complex cases. But the complicated part, the part that's most expensive, is on the structural integrity of it. So we are trying to optimize that part. Usually, what people would do is people would get to a solution that they like, and then they'll leave it running for a while and come back later to see the results. So basically, it usually takes some time. But basically it's usually done after the user has already set some constraints and already reached close to a desired goal. I don't know, Diana may know the exact numbers. I don't remember the exact numbers. She's also here. If you remember the exact numbers, I don't know. But it's in the order of minutes to hours, depending on the model.
For the, can you hear me?
Yes.
Yeah, for this Aquarium design, it took about half an hour.
Okay.
Okay, thanks. Well, my second question is that from the slides, it seems that the binary images are relatively simple. So if the front, side, and the top views are very complex with so many small or fine details, so how about the final performance? So will your method have the ability to recover or generate the fine details?
That's a good question. So for efficiency, should be about the same, because based on the voxel size and things. But for quality of the result, if you have lots of little details, it may lead to different parts being snapped off. So then if they're snapped off, then they're not part of the final design. So it does require the shapes to be relatively organic and mostly smooth. And that's usually the case with architectural buildings. Usually you have this very nice organic shape that you want to represent. Because if you don't, the building would also not look very interesting. You would have structural problems and so on, right? So it's usually for smooth organic shapes. Maybe you can have one or two details here and there, like for example, the head here of this bird. But if they are very inconsistent across the different views, then yes, you could run into problems. So you could have it in some cases, but generally you would want them to be relatively smooth. Yeah.
Okay, I see. Well, maybe let me ask the last question.
Okay, sure.
So from your introduction, I see that the direct output of your algorithm is the voxel model.
Yes.
So when you design your method, have you ever considered to directly output the mesh model? Because
very good question. Yes.
Yeah,
because that's what we want, right?
More details.
yes, and also that's what we want at the end. Yes. So the reason, or at least one of the major reasons we used the voxel model, it was because it was easier to simulate, especially issues with the stress on different regions. So that was one thing that made it easy. Also the intersection was easier to compute. It's just which voxels are inside and outside the models. So it was partly for efficiency purposes and also for simplicity of the algorithm and defining the algorithm. We feel that if the models are large like this, then doing voxel and then converting to mesh, we don't lose that much in quality, especially since we do the smoothing anyway to try to keep the model smooth and the roofs flat, right? So we don't lose too much, and we can control the resolution of the voxelization. Of course, the higher the number of voxels, the slower, but that's controllable. So at the extreme, they can be very detailed even in the voxel case. But yeah, it was a combination of simplicity, efficiency, and adaptability of the algorithms that we were considering. Yeah.
Okay, I see. Well, it seems that there are no further questions yet.
Okay. If anybody has any more questions, feel free to email me also, get in touch, or also Diana, who's here. This is mostly her PhD work, the one that I presented today. So yeah, so feel free to get in touch. I'm happy to discuss more if anybody's excited to talk about this.
Okay, that's all for the first talk.
Okay, thank you very much.
Thanks, Professor Sander again.
Thanks. Let me stop share here.
Yeah.
Okay.